Hi, this is Schwartz from MasterMathMentor.com. This is video BC23. The topic is Series, Convergence, and Divergence Review, and it covers the BC Manual pages 113 and 114. You are given an infinite series, and you wish to determine whether it is convergent or divergent. Let's review the steps in order. First, if it isn't already in this form, you must put the series into sigma notation form. Summation n equals 1 to infinity of a sub n, or summation n equals 0 to infinity of a sub n. You need to recognize special patterns and special groups of integers, such as their squares, their cubes, and their factorials. Our first step is usually the easiest and the quickest, the nth term test. You ask yourself, does the limit as n approaches infinity of a sub n is equal to 0? If the answer to that is no, then summation of a sub n diverges and you're done. If our series passes the nth term test, then we look for a special form. Is it in the form of a geometric series? And to answer that, you ask yourself, does a sub n in the form of ar to the n? If that is true, then you ask, is the absolute value of r less than 1? If the answer to that is yes, then the series summation a sub n converges. If the answer to that is no, then the series a sub n diverges. If this wasn't a geometric series, then ask yourself whether it is a p-series. Is this in the form of a sub n is equal to k over n to the p? If the answer to this is yes, then ask yourself, is p greater than 1? If that is true, then the series a sub n converges. If it is false, then the series a sub n diverges. If this is not a p-series, then ask yourself whether it's an alternating series. Is the form a sub n equals negative 1 to the n of some b sub n, or a sub n equals negative 1 to the n sub n plus 1 of b sub n? If that is true, then it is alternating. Ask yourself if b sub n plus 1 is less than b sub n. The terms are getting smaller. If the answer to that question is yes, then summation of a sub n converges. If the answer to that is no, then you need to ask yourself whether this is a telescoping series. Whether when you take the terms and add them together are terms canceling. If that is true, then summation a sub n also converges. And if the answer to that is no, then a sub n, the series a sub n diverges. If this is not an alternating series test, then we're going to have to look at our special tests. Other teachers might disagree, but this is the order that I would use to determine whether series are convergent if they are not in the forms on the previous page. The first test I like to use is the ratio test because it works with the biggest range of series. You ask yourself whether the limit, as n approaches infinity, of the absolute value of a sub n plus 1 over a sub n, if it is not equal to 1. If it is not equal to 1, then you are definitely going to get a conclusive result. If it is not equal to 1, then ask yourselves whether the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n is less than 1. If that is true, then the series converges. If that is not true, that means it has to be greater than 1, and therefore the series diverges. If you've gotten to this next step, it's because the ratio test gave a result of 1 and was inconclusive. So you go down to the limit comparison test. You choose some other series b sub n and look at the limit as n approaches infinity of a sub n over b sub n, which, if is finite, will give you a value of c, and we're interested in whether c is greater than 0. If the answer to this question is yes, then you look at summation of the limit as n approaches infinity of summation of b sub n, and whether that converges or not. If the answer to that question is yes, then the A series converges. If the answer to that is no, then the A series diverges. Next, we look at the root test. We ask whether the limit as n approaches infinity of the absolute value of the nth root of a sub n, whether it is not equal to 1. If the answer to that question is yes, then ask whether that is less than 1. If it is, then your A series converges. If no, your A series diverges. Finally, we reach the integral test. There are a very small range of series that will resist all the previous tests and yet will give a result with the integral test. We look at a sub n is equal to some f of n, and we assume that it is a continuous positive and decreasing function on the interval k to infinity. So we then look at the integral from k to infinity of f of x dx and ask whether that is convergent. If the answer to that is yes, then our series converges. If the answer to that is no, then our series a sub n diverges. I have not mentioned the direct comparison test, as it is rarely needed. All the other tests are usually much better, and you sort of have to be desperate to use the direct comparison test. However, it is helpful with some expressions involving trig, using the fact that the sine and cosine of any number is less than 1. We will see one of these in the example problem. For the following series, we will first expand them. After we do so, reflect on whether, if you just had the expansion, you would be able to generate the general term. Most likely you would not, as finding the pattern can be quite difficult. Once you do so, determine whether each series is convergent or divergent using an appropriate convergence test, and then note whether other tests are possible. One reads summation n equals 1 to infinity of n squared minus 4 over n squared plus 2n. Our terms are negative 3 over 3 plus 0 plus 5 over 15 plus 10 over 24 plus dot dot dot. The easiest test to use here is the nth term test. If we look at the limit as n approaches infinity of n squared minus 4 over n squared plus 2n, that is equal to 1, and since it's not equal to 0, it is divergent, and we can stop right there. Number 2 reads summation n equals 1 to infinity of 1 over n squared plus 4. Our terms are 1/5 plus 1/8 plus 1/13 plus 1/20 plus dot dot dot. The easiest test to use here is the limit comparison test with 1 over n squared, which is a convergent p-series. The limit as n approaches infinity of n squared over n squared plus 4 is equal to 1. And since this limit exists, our series will do with what 1 over n squared did, which is to converge. Note that we could also use the integral test because we can integrate 1 over x squared plus 4, getting an inverse tangent. Number 3 reads summation n equals 1 to infinity of negative 1 to the n times n plus 1 all over n squared plus 2n. When we expand it, we get negative 2/3 plus 3/8 minus 4/15 plus 5 over 24 minus dot dot dot. This is an alternating series. So we start with the nth term test, looking at the limit as n approaches infinity of negative 1 to the n times n plus 1 over n squared plus 2n. And since this is bottom heavy, our answer to this is 0. Our terms are definitely decreasing, so therefore this is a convergence series. In number 4, we have summation n equals 1 to infinity of the quantity 4n over 100 plus 2n, quantity to the n. And this is, when expanded, 4 over 102 plus 8 over 104 squared plus 12 over 106 cubed plus dot dot dot. We will use our nth term test and look at the limit as n approaches infinity of 4n over 100 plus 2 raised to the n. And we end up getting 2 raised to the infinity, which is infinity. So this is clearly divergent. And we also find that the root test, because of the nth power here, will work very well. Number 5 reads summation n equals 1 to infinity of 1 over quantity n plus 1 times the square root of the natural log of quantity n plus 1. Expanding, this is 1 over 2 square root of natural log 2 plus 1 over 3 square root of natural log 3 plus 1 over 4 square root of natural log 4 plus dot dot dot. This is one of these rare problems that all our tests fail, but the integral test will work. We integrate the expression 1 to infinity of dx over x plus 1 times the square root of natural log of x plus 1. Integrating, we get 2 square root of natural log of x plus 1 evaluated from 1 to infinity, which is equal to infinity. And therefore, since our answer is infinite, then this is a divergent series. Number 6 reads summation n equals 1 to infinity of 3 to the n times n factorial over n plus 1 factorial. Expanding, we get 3 halves plus 9 thirds plus 27 over 4 plus 81 over 5 plus dot dot dot. This is a good example of why it is a good idea to expand your expression. It is clear that the denominator is much simpler than it appeared. Since we have factorials, we will use the ratio test, and we look at the limit as n approaches infinity of the absolute value of 3 to the n plus 1 times n plus 1 factorial over n plus 2 factorial times n plus 1 factorial over 3 to the n times n factorial. We have to worry about the 3's and we have to worry about the factorials. For the 3's, 3 to the n plus 1 over 3 to the n simply gives us 3 upstairs. We have an n plus 1 factorial over an n plus 2 factorial, and that will give an n plus 2 downstairs. We have an n plus 1 factorial over an n factorial, and that will give an n plus 1 upstairs. So we have the limit as n approaches infinity of the absolute value of 3 times n plus 1 over n plus 2, and that is simply equal to 3. And since our result is greater than 1, this is divergent. Number 7 reads summation n equals 1 to infinity of 4 to the n times n to the 4th over n factorial. When expanded, this is 4 plus 16 times 16 over 2 plus 64 times 81 over 6 plus 256 plus times 256 over 24 plus dot dot dot. With the factorial, this problem is a prime candidate for the ratio test. We look at the limit as n approaches infinity of the absolute value of 4 to the n plus 1 times n plus 1 to the fourth over n plus 1 factorial times n factorial over 4 to the n times n to the fourth. Three things to be concerned with here: the n's, the 4's, and the factorials. There's one more 4 upstairs, so we have a 4 in the numerator. We have an n plus 1 to the fourth over n to the fourth, and that is simply 1, and an n factorial over n plus 1 factorial, giving n plus 1 on the bottom. So we have the limit as n approaches infinity of the absolute value of 4 over n plus 1, which is 0, and this is convergent. Students are always surprised at this result because they believe that the numerator is much more powerful than the denominator. In the first few terms, we can see how the numerator is exploding while the denominator isn't. However, a factorial is ultimately more powerful than all the powers of n or n to any constant. Eventually, the denominator will get bigger. In this case, it will take 19 terms before this fraction gets below 1. In number 8, we have summation n equals 1 to infinity of 12 over 7 times the square root of n cubed. First, it is best to write this as 12/7 summation n equals 1 to infinity of 1 over n to the 3/2 power. Expanding, now we see that our series is 12/7 times the quantity 1 plus 1 over 2 to the 3/2 plus 1 over 3 to the 2/2 plus 1 over 4 to the 3/2 plus ... This is a convergent p-series, as the p is greater than 1. We could also use the integral test on this because the integral of 1 over x to the 3/2 dx can be integrated. Number 9 reads summation n equals 1 to infinity of the quantity 2 pi over pi plus e raised to the n power. When expanded, this is 2 pi over pi plus e plus 2 pi over pi plus e quantity squared plus 2 pi over pi plus e quantity to the third plus ... This is a geometric series, and it is divergent, as the expression 2 pi over pi plus e is greater than 1. We could also apply the root test here as well. Number 10 reads summation n equals 1 to infinity of sine of n over 2 to the n. This is sine of 1 over 2 plus sine of 2 over 4 plus sine of 3 over 6 plus sine of 4 over 8 plus ... As stated before, this is one of these rare problems where a direct comparison test actually works well. We compare it with the convergent geometric series 1 over 2 to the n, and realizing that sine of n will have values less than 1, some of them may even be negative. So sine of n over 2 to the n will always be less than or equal to 1 over 2 to the n. And therefore, by the direct comparison test, this must be convergent. In number 11, we have summation n equals 1 to infinity of tangent of 10 over n. Expanding, we get tangent of 10 plus tangent of 5 plus tangent of 10/3 plus ... We will do a limit comparison test with the divergent harmonic series 1 over n and look at the limit as n approaches infinity of 1 over n over the tangent of 10 over n. And this turns out to be 0 over 0. So by L'Hopital's rule, we look at limit as n approaches infinity of negative 1 over n squared over secant squared of 10 over n times negative 10 over n squared. The n squareds cancel, and we are left with the limit as n approaches infinity of 1 over 10 secant squared of 10 over n. Plugging in our infinity, we get the limit as n approaches infinity of 1 over 10 secant squared of 0, and that is equal to 1/10. And therefore, this is a divergent series. Number 12 reads summation n equals 1 to infinity of 4 to the n over 2 to the n plus 3 to the n. Expanding, we get 4/5 plus 16 over 13 plus 64 over 35 plus 256 over 97 plus ... We will use the nth term test here, and it should be obvious that when we take a look at the limit as n approaches infinity of 4 to the n over 2 to the n plus 3 to the n, this is infinity. We can see that the numerator is getting bigger much faster than the denominator, as we see when looking at the terms. Interestingly enough, we could multiply the denominator by 1 trillion and it wouldn't make any difference. 4 to the n is ultimately more powerful than the terms in the denominator. Hopefully you have mastered the art of finding whether series are convergent or not. What you haven't done is try to determine why this is important. In our last sections in this course, when we examined power series, the reason for doing everything we have done up to this point will become crystal clear.